And the last for today is by Litt from University of Georgia, and he's going to tell us about integral aspects of arithmetic local system. So thank you.
Thank you so much for the introduction, Ellen, and thanks to the organizers for organizing this and for the invitation. It's really nice to be here virtually, although obviously I wish I could be there in person. So I wanted to talk about some integral aspects of arithmetic local systems or local systems that come from geometry. But before I do that, I just want to step back a little bit and just remind ourselves what is the point. And I know Ellen defined what it means for a local system to be arithmetic yesterday, but I want to recall that too. So suppose let's just start with a simple setting. So suppose you have a smooth variety over the complex numbers. And so I think the basic question that underlies a lot of this conference, for example, Ellen's talk and Mao's talk just now, is the following. It's the question of which are local systems where R is some ring, usually maybe over the complex numbers R might be Q or Z, but in general you might think about QL or QL bar or something like that. So the question is which are local systems on the analytification of this complex variety come from geometry? And I'll give a precise definition of that in a second, but for now, as in the last few talks, you should think this just means that these local systems show up in the cohomology of a family of smooth proper varieties over X, although really we'll discuss a slightly weaker condition. And why is this interesting? I think it's worth thinking about what this is actually saying about geometry. And it's, at least to me, it's interesting because it's an approximation of the following incredibly hard question, which is just can you classify all X varieties? So all varieties with map to X, or maybe all smooth proper families over X. So I like to think of this question as kind of a linearization of this one, which is maybe what we really care about. Although once you've drunk the Kool-Aid, hopefully this question is intrinsically interesting too. Okay, so I've asked this question, which is which R local systems come from geometry? And so let me give you the precise definition of come from geometry. So I'll say an R local system V on some variety X comes from geometry if there's an open subset U, so this is a Zariski open subset, which is dense in X, which I guess is automatic if X is smooth and connected, and a family Y over U, where this is smooth and proper, such that V restricted to U is a subquotient of Ri pi lower star of the constant sheaf R. So it's a subquotient of the local system whose fibers are the cohomology of this map. And maybe it's worth noting that we only require this on an open subset. There's not really, I think, any real reason to do that, except that it's a slightly stronger statement if you can prove something about all things which come from geometry in this sense. And then there's a few results I'll mention later, where we only know how to prove a local system comes from geometry in this sense. Okay, so the underlying question is which R local systems come from geometry? So this is a very restrictive condition. So let me just begin by reminding you with some example. So suppose you take your variety to be the affine line minus the origin, so GM. Then the fundamental group of this variety is just Z. And you can ask which representations of Z, viewed as the fundamental group of this variety, come from geometry. So such a representation is just up to isomorphism. It's just the same as giving a matrix, namely what the matrix that the generator of Z goes to. And it's sort of not so hard to see that a representation, a local system V rho associated to such a representation comes from geometry if and only if rho has finite image. Okay, so this says that these are very, so in other words, the generator of Z maps to a matrix of finite order. So this is obviously a very restrictive condition. There are plenty of representations of the integers which don't have finite image. So if you take a random matrix, that won't be the case. Okay, so what are the kind of structural properties of geometric local systems. So I think maybe it's sort of clear from this conference, and you know, if you're an expert, you know that these sorts of conjectures are totally out of reach. Like, we don't really know how to understand, like, how to prove that things come from geometry. So when you ask a question like which local systems come from geometry, maybe you want to ask like what extra structures or what extra properties do such local systems have. So I think maybe the most famous such property is that these local systems, if you're over the complex numbers, underlie a polarizable variation of Hodge structure. The main condition for this talk, as in Aladdin's talk, will be that these local systems are arithmetic. So let me remind you what that means. So suppose you start with a variety X over an algebraically closed field, and V is a locally constant QL sheaf on X. So here I mean a QL sheaf in the atoll sense. Maybe we should assume that L is not equal to the characteristic of K. Then what does it mean for this to be arithmetic? So loosely speaking, it means that this whole situation, including V, descends to a finitely generated subfield of your ground field here. So let me be precise. So you say this QL sheaf is arithmetic if there exists a subfield of K. So I'll call that little curly k, which is finitely generated over its prime subfield, and a model of your variety X over that small field, such that here you have a local system. So this is the representation. The local system gives you a representation of the atoll fundamental group, which I'll call rho V, and I'm going to ask that that local system extends to a representation of the fundamental group of this model. So there's a map like this, and we want an extension. So the existence of such an extension is arithmeticity. Okay, so the important property for this talk of geometric local systems, or local systems that come from geometry, is that they are arithmetic. And why is that? Well, if you have this situation here, a map from Y to U, well, these are varieties, and a map between varieties can be descended to a finitely generated subfield of the ground field. So one just descends the whole geometric situation, and thus one can descend the local system. Okay, there's a little bit of subtlety when one considers subquotients, but it's not so hard to deal with. Are there any questions about this notion of arithmeticity of a local system? Okay, so I think the big conjecture, which I've written as a question, because I'm not entirely sure if this is actually written as a conjecture anywhere in the literature, but I think it's a natural question to ask. Which is simply, does every arithmetic local system come from geometry?
Is it obvious that this has quasi-unipotent monodrama at infinity?
It's not obvious, but it's true. I mean, so I'll discuss this in a little bit, but Grothendieck's proof of quasi-unipotent local monodromy just applies to arithmetic local systems. Yeah, I mean, so that more or less Grothendieck's proof is take a local system which comes from geometry, observe that it's arithmetic, and then prove quasi-unipotence of monodromy for arithmetic local systems. All right, so I want to discuss a little bit of evidence for this conjecture.
I think this conjecture is sort of stated in Deligne's of A2, in the introduction to
yeah, I think maybe he states it over finite fields.
Exactly.
Yeah, I think that's right. Yeah, and in fact, Laforgue proves it over finite fields, so at least for curves. So for X a curve over a finite field, this question has a positive answer.
You have to say something about the determinant, don't you?
So because arithmetic local systems, it's a condition on the local system on a variety over an algebraically closed field. So what you're really saying is that if you have a local system on X space changed to FQ bar, which is arithmetic, meaning it descends, then it comes from geometry. And so there's a determinant condition, I think, on the descent. But once you pass to the geometric fundamental group, I mean, automatically the determinant is torsion. I think so. So arithmeticity implies that a rank, if you have a rank 1 arithmetic local system, it automatically is torsion determinant. If you're over algebraic closed. So yeah, so maybe I should, strictly speaking, write X is a curve over FQ bar, and maybe that answers the question. So this is an output of Lefort's work on the Langlands program for function fields. Okay, and I think this is more or less the only situation where we have such a good answer. I mean, there's a result of Snowden and Zimmerman where they show certain, for example, rank 2 arithmetic local systems come from geometry, but this is not so hard to see in rank 1. It's just the statement that rank 1 arithmetic local systems are torsion. But other than that, I think we know essentially nothing about this question. Please correct me if I'm wrong. So the other, I think, major evidence for this this conjecture is that arithmetic local systems satisfy some of the kind of arithmetic and p-adic Hodge theoretic properties that one would expect for local systems coming from geometry. So if V is an absolutely irreducible arithmetic local system over a number field, or so on a variety over the, let's say, on X, which is a variety over a number field, then, well, first of all, it's not so hard to see that V, well, the statement is that, this is the statement proven by Aluju and recent work of Petrov, who I believe is in the audience here, is that V, so the fibers of V, which are now Galois representations of the absolute Galois group of the number field, are geometric in the sense of Fontaine-Mazer. At least up to twist. So what does this mean? This means that these Galois representations are unramified almost everywhere, and that's not so hard to see. And then the hard work, which is recent work of Petrov, using the p-adic Simpsons correspondence of Liu and Zhu, and then Petrov showed that these are de Rham at primes above L. So here V is a QL local system. So I think this is fairly strong evidence for this question having a positive answer, saying that, I mean, like, how else would you show that it's false? You would like look for some condition like this to fail, and we know this condition does not in fact fail.
Does that extend to QL bar here? Yes.
Instead of, yeah, I mean, you could replace QL with any finite extension in the proof. I mean, Alexander, please correct me if I'm wrong, but at least that's how I understood that.
Right, and in fact, you need to assume that it's irreducible after you extend the coefficients to QL bar.
Yeah, so it has.
Yeah.
Yeah. So yeah, so I mean, that said, I think there's a I think the answer is yes, as long as you put this absoluteness here. All right, are there any questions about this statement?
Yeah, what about, so this is for absolutely reducible representations. What about ones which aren't? Is there evidence that the conjecture is true for those too? I thought maybe not.
I think you just have to probably change up to twist here to see that there's no real obstruction to being true, right? Like what you would do is you'd extend so it's a direct sum of absolutely irreducible pieces, and then maybe you'd have to twist each of those parts. But again, I mean, you'd just be twisting by a character of the absolute Galois group of the base. So in terms of curves over, in terms of the result for local systems on the geometric curve, I don't think there can be any obstruction coming from this sort of computation or this sort of result.
And one more question. So the result of Petrov, he can also answer, is for curves, or is that in higher dimension as well? Or?
I think it's for arbitrary smooth varieties.
Yeah, that's right.
Thank you very much. Very nice.
And
Yeah,
when you do this dévisage that you just explained, if it's not absolutely irreducible, do you know that the individual constituent pieces will still be arithmetic?
Yeah, that's not, as long as it's semi-simple, that's not so hard to see. And so, yes, maybe I think I did not assume that arithmetic local systems are semi-simple, so maybe let me actually,
okay, that's what was worrying me.
Yeah, that should be in the question. Sorry. Otherwise, you need some condition on the extensions that show up.
Right.
Yeah. Any other questions about this? All right. So the question I'm interested in, and I think this is interesting from the point of view of the previous question, is just what conditions does arithmeticity impose on a local system? So I think Adrian asked about this recently or a few minutes ago. So the first basic test, like if you want to test this question, if you want to test whether every arithmetic local system comes from geometry, you should take every property of geometric local systems and check that it's true for arithmetic ones. And so the first maybe obvious test is that you want to know if local monodromy is quasi-unipotent. And as I said in answer to Adrian's question, this is indeed the case for arithmetic local systems. And in fact, I mean, this is at least one of the proofs that local systems which come from geometry have quasi-unipotent local monodromy. So as I explained, Grothendieck proves this for arithmetic local systems, and hence it's true for geometric local systems. Okay, and there are a number of other questions you can ask about geometric local systems, and you can try to verify them for arithmetic local systems. Maybe it's worth noting, for this talk, I'm mostly interested in going the other way. I want to explain, I think arithmetic local systems are interesting because they tell you things about local systems which come from geometry. So in my view, the search for new conditions that arithmeticity imposes on a local system is interesting because it tells you about structural properties of maps between algebraic varieties. So for the purpose of this talk, I want to talk about integral restrictions imposed by arithmeticity. So for example, if you have a arithmetic ZL local system, can you say anything interesting about what happens when you reduce it mod L? Or mod L to the billion or something like that. Or if you have two arithmetic local systems which are the same, mod L squared, what can you say about them? Are their properties related or something like that? Okay, and as far as I know, I think this is a fairly, a kind of poorly understood area. I don't think that we know so much about the integral properties of even local systems which come from geometry. Okay, so let me sort of give the flavor of what I mean by describing a theorem, and this will be the first of several theorems in the talk. So this is actually a combination of several old and new results due to myself and then sort of recent in progress joint work with Borys Kadets, who's a postdoc at UGA. So let me explain this statement. So suppose I have a normal variety over a separably closed field, which I'll call X, and the separably closed field is K. And I take a prime which is not equal to the characteristic of K. So then the statement is that there's some number. This doesn't have to be an integer. It can be a rational number, for example. So that which depends on X and this prime L. Such that if you have a representation of the geometric fundamental group, if you'd like, or a local system, which satisfies the following two conditions. So first of all, this is a semi-simple arithmetic representation. So in other words, the corresponding local system is semi-simple and arithmetic, meaning it descends to some finitely generative subfield of K. And moreover, rho is trivial mod L to the n. So this n could be, for example, 1/2. So you could be saying something like it's trivial mod the square root of L. Then what's the conclusion? Then the conclusion is that rho itself is trivial. So there's some absolute constant, which detects triviality of a local system after reducing mod L to that constant. Okay, so this is Yeah, so let me tell you a little bit more about the constant. So in characteristic P, we don't have very good control over it, but in characteristic 0, we can say quite a lot. So in characteristic 0, these constant n of xl can tend to 0 as L tends to infinity.
Really?
Yes.
Wow.
So in particular, this says, and I'll make this concrete in a second. This says, for example, if you fix x and take L very large, any arithmetic local system which is trivial mod L is in fact trivial. So I think that's a fairly strong statement.
Or mod L, square root of L.
Yeah, even or mod the square root, or in mod the billionth root of L. Yeah. Right.
Yeah, Daniel, we are really looking at local systems here, not at representations. So we say if the local system mod L is trivial or mod something, then the initial local system is trivial, but not the representation. Or is that exactly the same statement?
I think it's the exact same statement.
Okay.
Yeah. Are there any questions about this statement? I mean, I'll spend some time unpacking it and discussing similar statements also. Okay, so of course, this implies that if you come from geometry, that representations should come from geometry satisfy the same statement. Okay, so let me give you a kind of concrete, the concrete corollary. So suppose you have a normal complex variety, then if you just look prime by prime, you get the following statement. So there exists some number, n, which only depends now on x, such that if you have a representation of the fundamental group into, let's say, GLN Z bar, which comes from geometry, and it's trivial mod m for some, this should be mod an integer m, for some m bigger than your given number, then rho is trivial. So for example, so note, for example, that this capital N is actually independent of little n here. So for example, what is this saying concretely? So one concrete statement you can extract from this is that if you have an abelian, that no abelian scheme over x, which is not isotrivial, has full M torsion for any m bigger than n. So no abelian scheme of any dimension. Yeah. So are there any questions about this? And how do you extract that? You extract that by taking rho to be the local system arising from the first cohomology of your abelian scheme. Are there any questions about this statement?
Can you say a few words? Sorry, can you say a few words about the dependence of n on geometric invariants of x? Or
yeah, so that's a really good question. So I think there's some sense in which this statement is not optimal. So here n. I mean, let me go back to this statement. So here n just depends on if you take a descent of x to a finitely generated field, it depends on the Galois action on the first homology of x. There's some subtlety in characteristic P. One has to cut by curves and do some devisage, but in characteristic 0, that's the dependence. The sense in which I think this is not optimal is that one really expects this maybe to only depend on the birational class of x. So for example, if x is a curve, maybe with slightly different uniformity, one should expect this to only depend on like the gonality of the curve. And I'll describe a result along those lines at the very end of the talk. I think this kind of uniformity, where you get uniformity which doesn't depend on the dimension of the representation in question, you can't expect only birational dependence. So, but I think if you, my guess, and as I said, I'll describe a result along these lines at the end of the talk, is that if you allow dependence on the rank of this representation here, you probably get better birational dependence. Does that answer the question?
Yeah, it answers the question, but then I have a second question. It's because you said it depends only on the first homology. So suppose the first homology is trivial with Z coefficient.
Yeah. Oh, yeah. Sorry. I should have said it depends on the first homology of a curve whose pi 1.
Okay. Okay. Sure. Okay.
Sorry about that. Yeah. Yeah. Sorry. And all these results you immediately reduce to curves, and then it.
Okay.
Yeah. All right. So this is. I mean, let me talk about this a little bit. So this n is pretty explicit. So for example, for p1 minus 3 points, I think you can take n to be you can take n equal to 13. And maybe just a remark, I mean, this result is really kind of prime by prime. So for example, so for example, you can take n of x5, meaning like if you want to check if something is trivial mod 5 to the something, you can take this to be this is less than 1. So in particular, any representation of pi1 of p1 minus 3 points, which is trivial mod 5, is trivial if it comes from geometry. So I wanted to mention this actually because of the question. Sorry, who asked that question? Was it Johan, or I wasn't able to see who asked it.
It was Bruno.
Oh.
Bruno.
Yeah, sorry.
It was me. Sorry.
Yeah. So Bruno asked about sort of the dependence on x, and I mentioned that I don't really expect a statement of this form to kind of only really depend on geometric invariance. I think it's like a genuinely arithmetic statement. Because so I just told you that there's no representation of pi1 of p1 minus 3 points, which comes from geometry and which is trivial mod 5. But there are genus 0 curves which have representations which come from geometry, which have local systems which come from geometry and are trivial mod 5 but are non-trivial. And the example here is y of 5, the modular curve parametrizing elliptic curves with trivial 5 torsion. So this is a genus 0 curve. But this n of y of 5 is obviously bigger than 1, because if you look at the representation, the local system coming from the tautological family of elliptic curves over that's trivial mod 5, but the representation itself is highly non-trivial. And the proof actually sees this. So the proof of this statement, or really the previous theorem that one derives it from, sees somehow the Galois action on the cusps if you just specialize to the genus 0 case. And here the point somehow is that the cusps of the modular curve y of 5 that they generate a field extension which contains like the fifth roots of unity.
Can I have a naive question? For example, if you apply this to p1 minus 4 points, can you actually say classify Borys numbers like in previous talk?
I'm sorry, I don't remember the definition of Beauville number.
Well, the definition was, this was classification of elliptic vibrations that were smooth everywhere outside of 4.01 infinity and lambdas. So here it looks like this lambda is could be somehow be restricted by your conditions.
It's possible. I mean, somehow like the statement that the residual representation is trivial seems very strong to me if one wants to understand elliptic vibrations. So I'm kind of skeptical of an application like that. Like typically an elliptic vibration will not, like with very rare exceptions, it will not have any trivial residual representations, right? I mean, that's somehow what this theorem is saying. But it doesn't really tell you anything. I mean, later on, I'll mention some things which might say stuff about residually non-trivial local systems. So, for example, if you have a elliptic vibration with non-trivial L torsion, but this theorem at least doesn't at least in my opinion say anything about that. Does that answer your question, Adrian?
Yes. So this was very naive, as I said. So
no, yeah. So maybe it is worth mentioning though. I mean, so you asked like, what if you take p1 minus 4 points? Like, what can you say? So here this number n will. So if you take p1 minus 0, 1, infinity, and lambda, this number n will really depend on lambda. So like on the arithmetic properties of lambda. So for example, if lambda is q lies in q, you'll always get this nx5 less than 1. But if lambda lies in a big cyclotomic extension q, it can grow. And this example sort of shows that's actually necessary for a sharp statement. Okay, and then the remark is maybe worth noticing is that n doesn't depend on the rank of the representation here, on the rank of rho. So on this number little n here, which I think is sort of a strange uniformity, but I kind of expect it to be useful for applications. All right, are there any questions about this corollary before I move on? Or the theorem that it's a corollary of? So maybe it's worth noting, I mean, this is a combination of several theorems. So this resultant characteristic 0 I proved a few years ago, the characteristic P result is new and requires some genuinely new ideas. So I'll describe some of those in a little bit. All right, so let me, now that I've given you a result, let me kind of situate it in some kind of conjectural picture. And I want to explain like what we kind of expect to be true, going back to Bruno's question, in terms of like how these invariants and how torsion behavior should depend on geometric invariants of the underlying variety. And then I'll tell you a little bit more about what we can prove. So I think, at least for me, a lot of the motivation comes from this old theorem of Mazur, which says that if you have an elliptic curve over Q, then it doesn't have a lot of torsion. There's a uniform bound on how much torsion it has. And in particular, he shows that the torsion, the number of rational torsion points of an elliptic curve over Q is at most 16. And in fact, he gives a complete classification of the possible torsion subgroups. So I think, for example, the only way 16 can be achieved is if you have a torsion subgroup of this form Z mod 2 times Z mod 8. And there's a massive generalization of this statement, which is due to Morel, which is that if you have K of a number field of degree D, then there's some integer n, depending only on the degree of the number field, so n only depends on D, such that if you have an elliptic curve over K, you get a similar bound. So the number of rational torsion points, EK tors, is bounded above by this number n. So I think, at least to me, like the sort of dream theorem, or one of the dream theorems one would want about integral aspects of local systems, is understanding the function field analog of this. So let me, in a little bit, I'll kind of try to give a precise statement of such a conjecture. And here it is. So I think this maybe gets to Bruno's question about what we expect the dependence of these invariants to how these invariants, how we expect them to depend on the geometric invariants of the situation. So this is some variant of the geometric torsion conjecture. I don't know if this exact conjecture has appeared in the literature, but I think it's reasonable to extract from what people have already conjectured. So suppose you have a curve over the complex numbers, which has gonality gamma. Let me remind you what gonality means. So this is the minimal degree of a non-constant map from X to P1. So for example, P1 has gonality 1, elliptic curves have gonality 2, etc. So then the statement is that there exists some integer n, which only depends on the gonality, so that's a geometric invariant, and another integer d, such that if you have a representation of the fundamental group of X into GLDZ, so this is the same D, which comes from geometry, then it has bounded torsion. So let me briefly explain what bounded torsion means. So you take your local system, you tensor with Q mod Z. So you should think if this local system was the H1 of an abelian variety, this is just the torsion of the abelian variety. So maybe let me write that down. So here you should think this is, so thought bubbles, you should think this is rational torsion, or sorry, this is torsion.
So the theorems were were general, but here you assume that X is projective, or
no.
So you assume that compactification of X has gonality gamma, or?
Yeah, but it's the same because of the evaluative criterion of properness. Yeah. So what you should think is this you have your local system. Imagine this V rho comes from the cohomology of an abelian scheme over X. Tensoring with Q mod Z is the local system of the torsion in the abelian scheme. So taking pi1 invariance is taking rational torsion. Sorry about that. And now I'm going to mod out by the divisible part. So this divisible part is coming from kind of constant isogeny factors. Okay, So the conjecture says that if you look at the part of the rational torsion, which isn't coming from constant isogeny factors, it should be uniformly bounded in terms of the geometric invariance of the situation. So in terms of the gonality and the dimension of your abelian scheme. Okay, and then this is a mild generalization to sort of arbitrary geometric local systems, which I think is plausible, although we certainly know nothing about it. Okay, so I mean, I think we don't know so much about this conjecture. Some remarks are that for if V rho comes from an elliptic curve, this conjecture is very easy. It's just the statement that modular curves have gonality tending to infinity with the level. So then this is the statement that the gonality of a modular curve tends to infinity as the level does. For abelian schemes, we know very little. There are some results from a couple years ago of Backer and Zimmerman. And then we also know some things about full level structure, which are due to Nadel, Huang and To, and Brunebar. And I mean, there's some intermediate results in there as well, but I don't claim that this is a exhaustive list of what we know, but I think this is a reasonable summary. I think in this generality, we know very little. I think really for abelian schemes, which are maybe not of GL2 type, I think as far as I know, this conjecture is totally open. Yeah. So this is, I think, this is sort of the most optimistic statement one could ask for, and of course, you could drop, you could replace this with another field and then ask about ZL representations, and if you replace this QL with Q mod Z with a QL mod ZL, you would get an analogous conjecture. All right, so the other main conjecture I want to discuss is some variant of the geometric Frey-Maser conjecture. So the Frey-Maser conjecture says that if you have two elliptic curves with the same L torsion for L very big over a number field, then they should be isogynous. So this is a translation of that to local systems. So suppose you have a curve X of gonality gamma, then the conjecture is that there's some absolute constant n, such that if you have two representations of the fundamental group, which come from geometry and are the same mod some big number m, so m bigger than n, which is only supposed to depend on the gonality in D, then the statement is that these two representations being the same mod m implies that they're the same mod q. And then for abelian schemes, you should think that this means that if the m torsion representations are the same, the abelian schemes should be isogynous. Kind of modulo constant parts. So maybe let me mod out by the traces here. And again, we know very little about this. I think as far as I know, the unique result about this sort of statement is due to Backer Zimmerman for abelian schemes of GL2 type. So please, if someone in the audience has proven something about this and I missed it, let me know. All right, are there any questions about this? So I think these are the sort of dream statements one would want. I don't know how to prove anything with this kind of uniformity, in particular with uniformity in the gonality. It seems very hard with the methods I know how to use, but I can prove some kind of weak statements. So let me tell you some of those. So here's a theorem I proved a couple years ago. So suppose you have a curve over a separably closed field and a prime which is not equal to the characteristic of the ground field. Then the statement is that the set of semisimple arithmetic representations of the étale fundamental group into GLN QL bar, so modulo conjugacy, is discrete in the l-adic topology. So what this means is that if rho I is a set of semisimple arithmetic representations whose traces are converging to the traces of some rho uniformly, this implies that the sequence of rho i's is eventually constant. So that's the meaning of this discreteness. So discrete in the uniform topology. Let me briefly unpack that. So if you have a representation, its trace gives you a function on this group, and the statement is that if these functions converge to this function uniformly, then this sequence of representations, well, modulo conjugacy, is eventually constant. So meaning these for I very large, these rho i's are all isomorphic to each other are all conjugate to each other as representations. Are there any questions about this? So I'll explain in a second how this is some kind of weak form of this Frey-Maser conjecture that I just mentioned, which says that representations are determined by their residual representations. But let me just remark on a sort of simple consequence, which I think is very appealing. So with X as above, if you look instead of representations into QL bar, if you look at representations into a finite extension of QL, so K, then the statement is that the set of semisimple arithmetic tame representations, so from this group into GL and K, which remember is a finite extension of QL, is finite up to conjugacy. So maybe just a remark is that I view this as an analog of Deligne's theorem. So Deligne showed that if you look at the set of local systems which underlie z-local systems which underlie a variation of Hodge structure on a smooth complex variety, then the set of a given rank is finite. Sorry, a polarizable variation of Hodge structure. So I view this as some analog for arithmetic local systems. It's saying that if you look at local systems valued in a finite extension of QL, that set itself is finite as long as you fix the rank. Are there any questions about this statement?
And so could you replace tame by a sort of bounded wild inertia?
I'm sure the answer is yes, but I don't know how to do it. My guess is that if you replace it with bounded Swan conductor, you're fine. But I haven't thought about it really hard. Yeah, let me say I'm 99% sure it's true. Yeah, maybe I shouldn't put it's either true or it's false. So the probability is either 0 or 1. But yeah, I think it's probably doable. Let me know if you want to discuss it, Remy.
And here again, do you have any kind of uniformity? So suppose that X varies in the family of curve.
No kind of uniformity at all. I mean, I can tell you what. Yeah. So you might ask like what, like, yeah. I'll draw a picture in a little bit of this. So you might ask like, given a representation, this is saying there's some like small ball around it where there's no other arithmetic representations, right? And you might ask like, what is the size of that ball? And like, again, you would expect it to depend on geometric invariance of the situation, but I don't know how to prove something like that. I mean, at the very end, again, at the very end of the talk, I'll describe some result with some kind of uniformity along those lines, but I think that's like the really big missing piece in this story.
Mm-hmm. Thanks.
Yeah, so let me just remark, I mean, the corollary is a very weak form of Frey-Maser, meaning with no dependence on with no kind of uniformity and geometric invariance of the situation, which is that if you have a normal variety over a separately closed field, and L is not equal to the characteristic, then how should I say this? Then if you have a representation which is semisimple arithmetic and whose residual representation is absolutely irreducible, then the statement is that there's some form of this weak Frey-Maser conjecture is true. Namely, there exists some integer n, so that if you have another rho prime, which is semisimple arithmetic, and the same mod L to the n, then rho is isomorphic to rho prime. Sorry, is conjugate to rho prime. Yeah, by this isomorphism symbol, I mean conjugate is representations. So the statement is that arithmetic representations, which are absolutely irreducible are determined by what they are mod L to the n. And this is just there's no additional content to the statement besides this theorem. It's just saying that if you have a residually absolutely irreducible representation, it's determined by what it is mod L to the n.
Daniel, excuse me to interrupt you briefly. Why do we need the condition on the residual representation here?
Yeah, so what you need to do is you need to translate some statement about traces to a statement about isomorphism of representations. And so
yeah, but yeah.
So all we know is that the traces are very close together. I mean, if you want an integral statement here, if you only want a rational statement here, I don't think you need this. The issue is, like, a priori rho and rho prime could be two ZL lattices in the same QL representation, which are not isomorphic as ZL representations, but that can't happen in the residually absolutely irreducible setting.
But here, maybe I cannot read correctly here. I mean, then there is an n, and rho is the same as rho prime mod L to the power n, right? Mod ln.
Yeah, that's right.
Why? I mean, it should not play any role that you start with a representation with an absolutely irreducible residual representation. Because finally you look at mod L square, mod L3, and so forth. So at some point, well, it doesn't matter.
I mean, this n I want to be independent of rho prime. So otherwise, it's sort of not a contentful statement. So at least I wasn't able to prove this statement without some residual irreducibility. It's possible something like, I don't have a counterexample, so, but I would expect one needs something like this. I think that, I mean, if you're okay with them being rationally isomorphic, then I think you can drop this assumption. Yeah. Okay. So let me just briefly draw a picture of the situation. So start with some absolutely irreducible residual representation, just for simplicity. And then this thing has a deformation ring. So our rho bar here is the deformation ring of rho bar. If you're not in the absolutely irreducible setting, you can use Chenevier's pseudo representations, as Hélène mentioned in her talk. But maybe this is a more familiar picture. So the rigid generic fiber of this ring parametrizes like QL bar representations, which lift this given residual representation. And so what is discreteness saying? Discreteness is saying that if you look at the discreteness of arithmetic representations, is saying if you look at the sort of periodic points of the Ly action, those are precisely arithmetic local systems. Then they're discrete here. That said, there are typically infinitely many periodic points. One can prove that using Gates-Gordy's solution to de Jong's conjecture. But this is saying they don't accumulate. They sort of only accumulate near the boundary of this open disk. So for example, this says that if you have any closed disk inside, there are only finitely many arithmetic representations. So that's one way to think about this finiteness statement I stated for representations into finite extensions of QL. And then I think someone asked about sort of uniformity in geometric invariants. So I think the big open question is, you know, around each of these points, one can draw a ball, but there are no other periodic points. And the big question is, what is the radius of this ball? And I mean, in characteristic 0, I can give an effective bound on the size of this radius, but it doesn't have the sort of good geometric, like dependence on the geometric properties of the underlying situation that one would want. Okay, so let me briefly discuss a little bit about the proof of some of these statements, and then I'll discuss a sort of new result with some better dependence on the underlying geometric situation. So let me just briefly describe this situation. This is the very first theorem I stated, which, let me remind you, you have a normal variety over a separately closed field, L a prime not equal to the characteristic. And then one wants to say that there's some absolute constant which only depends on the variety. so that if you have a representation which is trivial mod that constant, mod L to that constant, and semi-simple arithmetic, then it's trivial. And then moreover, there was some statement about these constants tending to 0 as L goes to infinity, which is a sort of much stronger statement. It's not just a prime by prime statement. So I want to give you a proof idea in a very simple situation, which is new though. So I want to describe it. So let's look at the situation where X is a smooth affine curve. One can immediately reduce to that situation, and moreover, the algebraic closure of a finite field. Some notation. If you look at the pro-L fundamental group of X, that's just a free pro-L group because of this affineness assumption here. I'll let ZL bar of this pro-L group be the group ring of this free pro-L group. So abstractly, that's isomorphic to a non-commutative power series ring over ZL bar. So this is a little computation you can do if you take the pro-L group ring of a free pro-L group. It's a non-commutative power series ring. And then finally, I'll consider inside of the ring of non-commutative power series over QL bar. So that's what one gets when one base changes to QL bar and completes with respect to this ideal, the Xi's. I'm going to look at the ring of power series which are convergent, meaning in some disk, which just means that the coefficients of some monomial don't grow too quickly in terms of l-adic absolute value. So what's the property this ring has? Well, suppose you have some representation of the fundamental group. That's just the same as long as the representation has pro-L image as a map of rings from this group algebra to matrix algebra. This matrix algebra with coefficients in ZL bar maps to the matrix algebra with coefficients in QL bar. And typically this map won't extend to a map on the full power series ring over 2L bar because there are convergence issues. But if you're trivial mod L to the n, you'll get an extension like this to this ring of convergent power series. And everything here is totally canonical. So in particular, there's if you have an arithmetic representation, there's a Frobenius action on this whole picture, making the diagram commute as a diagram of rings within an automorphism. So the goal is going to be to diagonalize this Frobenius action on this ring of convergent power series. So I mean that in some topological sense. This is a Banach algebra, and I want to find eigenvectors for Frobenius with dense span. Okay, and if we can do that, we basically win. Once you understand the eigenvectors here, well, they have to map to eigenvectors here, and this is a finite dimensional vector space, so there cannot be a lot of eigenvectors. So this is saying most eigenvectors have to go to 0, which will eventually show that the representation is unipotent, and a semi-simple unipotent representation is trivial. Okay, so let me just briefly talk about this goal of diagonalizing the Frobenius action on this non-commutative power series ring. So there are 3 steps. So first of all, one needs some geometric input. So one shows that this action on the full ring of power series without any convergence condition is semi-simple. So this is a little bit of geometry because this action can have repeated eigenvalues. So it's not totally formal, but it's semi-simple. So now once what's
the geometric input here?
It's just understanding the weight 2 part of this ring. So somehow the only place where you could in principle have repeated where you have eigenvalues that are repeated and where it's sort of not obvious that you're semi-simple is the weight 2 part of this. This is sort of the pro-unipotent completion of pi1. And so that you have to split the Frobenius action on that weight 2 part. And it boils down to picking some Frobenius invariant paths, which you can do by the theory of weights. Okay, so now given that, one wants to solve an equation like Frobenius applied to some power series in the xi's is lambda times that power series. And in the commutative setting, there's a way to solve this equation. So you can somehow the issue is one tells you that you can solve it formally. There's there's some formal power series in these QIs which satisfy this equation, which are eigenvectors. And one needs to understand the radius of convergence. And Siegel gave a way of solving such functional equations. Assuming, so this is assuming so this is in the commutative setting. So in the commutative setting, and assuming some arithmetic statement, some arithmetic condition on the eigenvalues here, on the eigenvalues lambda. So we need the new input here is we need a non-commutative version of Siegel's theorem, and also it's also an l-adic version of Siegel's theorem. Siegel was working in the Archimedean setting, and then finally this arithmetic condition on the eigenvalues, and to check that we need to the l-adic version, so the l-adic version of Baker's theorem on linear independence of logarithms, which is due to Kunryu. So essentially, the input boils down to the statement that these lambda are algebraic numbers by the Weil conjectures, and then Baker and Yu show that algebraic numbers satisfy this arithmetic condition. So this is more or less the idea. Are there any questions about this? Sorry, I know it was a little fast. So the point is that there's a little bit of sort of actual arithmetic input here. Maybe it's worth noting. I mean, in fact,
what's the date of this work?
Of Yu's work or this?
No, of your work.
The statement in characteristic 0 is, well, it's just going to publication now, but it's a couple years old, and then in characteristic P, it's work in progress, so it should be out soon. Yeah. So this is not yet published.
Okay.
Yeah. So let me just finish by giving sort of one more new result. This is also work in progress. So I expect to be able to improve it a lot. So the goal is to prove an analog of the torsion conjecture for function fields. We can't quite do that yet. But here's what we can prove. So here, this is function fields over finite fields. So here's what we can do, and it has at least some kind of uniformity in the geometric situation. So the statement is that there's some integer n, which depends on L, Q, and D. So here L is the prime, Q is the size of our ground field FQ, and D is the rank of our representation, such that if you have an open subset of P1, so just a genus 0 curve, and a representation of its fundamental group into GLN DZL, which is, well, it's automatically semi-simple arithmetic because U actually lives over the finite field. If it's residually trivial, and it has a lot of torsion, so meaning the set of, when you go up to FQ bar, the set of fixed points here, mod the set of divisible stuff is very big, then the statement is that rho is trivial. So this is a sort of variant of the theorem I discussed earlier. The main difference is that we have the sort of correct uniformity in the geometric invariant. So here U can be any genus 0 curve, and we've proven the same kind of statement. The deficiency is that that we really need the representation to be defined over FQ. So this is sort of like the torsion conjecture over a number field, whereas the geometric torsion conjecture is something like the torsion conjecture over an infinite cyclotomic extension of the number field. So we can't say much about sort of arbitrary representations of geometric fundamental groups, but we can give something with at least approximately the right uniformity in the underlying geometric situation. All right, so I think that's all I wanted to say. So thank you so much for listening, and I'm happy to answer any questions.